Hi, my name is Levi Simons, and today I'm going to be talking about some recent work I've been doing in the field of light pollution and landscape ecology, and how light pollution is affecting ecosystems, at least in the coasts of Southern California. So just to give you an idea of what I'm going to talk about here is just the process it took to actually get the data to start studying this in Southern California. So building a model of what light pollution exposure is like on the ground, getting other types of environmental data to see how we can compare the relevance of light pollution to other factors in the environment, and then comparing our model for where we'd expect to see at least two key species, in this case, the western snowy plover and California grunion, in Southern California, given where light pollution levels happen to be recorded and how bright things are. And then I'll go into some of the mathematical modeling between how I ended up constructing this and evaluating all this. And at the end of it, just sort of what's the TLDR, what does this all mean? So here's a recent map, this is just a few years old now, of how bright the Earth looks like from space. And this is scaled to looking at fraction above natural light. So this is natural sky glow. So for pretty much all of the Earth's history, how bright it would look like. And as you can see, there are large parts of the Earth that are essentially unaffected by anthropogenic light. But as you can also see, we have large chunks of where humans live are extremely impacted by high levels of light pollution. So I just want to point here at the scale here. So this is the brightest areas, about 41 times natural levels. This is bright enough that in certain areas, so let's say Port of Los Angeles, Singapore, Tokyo, it is bright enough actually to trigger photosynthesis. Not a lot, but that's an astounding level of light that essentially you're just dealing with continuously. So a lot of work has been done in trying to figure out how significant light pollution is in ecology. And for the past few decades, all this work has been based on looking at remote sensing data. And by remote sensing, I mean those Earth at night photos you've probably seen. Like, how bright does it look like from space? But there's issues with using these measurements, or at least there's a lot of assumptions that have been made, and nobody had really tested them that much. And that is, if it's bright from space, is it really bright on the ground? Or how bright is it on the ground if it does look like it's bright from space? And there's a lot of factors that come into play. And one of the basic ones, just this idea of what's the difference between upwards radiance? So how much light is getting up into orbit versus what you're actually getting bombarded with on the ground. And that can vary significantly here just by changing the configuration of street lamps. So whether or not the light is just directed straight down versus just going all out into space. There's a lot of variation just by the arrangement of buildings and hills and other structures that are going to block or reflect light. You're also dealing with this idea of sky glow, which is just things reflecting off of humidity and just gases in the atmosphere, and reflectance off of surfaces, which is a big deal, especially in a lot of built urban environments, which we're dealing with. So one of the other major limitations is the spatial resolution of these light pollution satellite data sets is relatively coarse. So a lot of this stuff is based on spatial scales of approximately 750 meters on a side. You're probably wondering why it's that resolution. The answer is because these light pollution data sets were not ever constructed for the purposes of ecology. They were constructed to look at things like growth of cities, trying to infer economic indicators from light levels, that sort of thing. And 750 meter resolution is perfectly fine for that. But if you're a little creature scurrying around on the ground in coastal California, 750 meters is the size of your entire universe. And there's a lot of things get smeared out. The next thing is also that it's a simple day-night band. And what that means is that if we look at the sensors in these satellites, up until only very recently, it's starting to change, it just tells you whether or not there's light, and if there's light with a wavelength longer than 500 nanometers or not. And in particular, it's about 500 to 900 nanometers, which is roughly green light to near infrared, is what we're actually seeing with most current light pollution readings from space, which means anything with blue or violet light actually just doesn't show up in a lot of these data sets, which is a big limitation, especially considering the importance of blue light in regulating a lot of circadian rhythms. So to address this, at least in part, there was the model, which I showed you the Earth map from earlier, and it's to factor in using atmospheric scattering, models and combining that with what we know about where light is positioned from numerous readings of just ground-based measurements using what are called sky quality meters, which are just basic light sensors, we can estimate how much light you're actually getting exposed to from across the entire hemisphere of the night sky. So if you see here, there's just different models here looking at, okay, you have light coming from a source, it's going to get scattered in the atmosphere, and so you're going to get this sky glow across the horizon. And what you end up having to do is then integrating this across the entire bubble of the sky to get what you're probably getting exposed to. And this is a really useful technique. In fact, you can go online and look up the global map of what they generated. This is what it looks like for LA. Probably not too surprised that it's incredibly bright. Although what's really interesting is that it starts to drop off, and then there's areas over here just beyond the edge of this map when you get towards the north end of LA County where you can get the Milky Way on camera. So within the same county, we can go from triggering photosynthesis to, I wouldn't say absolutely pristine skies, but you can see shooting stars in the Milky Way. And if we just clip out what that looks like here on the coast, using our fancy color scale here, this is essentially what it looks like. So this is log of the world atlas data. So, and I'm using a log scale because usually vision actually goes logarithmically with the amount of light. And in order to start figuring out like how true is this, so how true is this model if we know how bright it is from space, how bright it is on the ground, I went out for about 7 months and hit up 515 locations along the coast, setting up a camera here, and I use a fisheye lens to get the entire hemisphere of the night sky so I could integrate all the light out of it. Although this one was not taken for data, this was just a really cool shot I took with friends up near the north end of Ventura County. And what I did is say, okay, I'm going to get readings on the ground compared to what we see from space and to start seeing how closely things can be predicted using just remote sensing data. Because as I can tell you from driving 6,500 miles over a 7-month period in Southern California, it's a lot of work to do this. So if you can build a model and you can just say like, hey, if it looks like this from space, this is probably what it looks like from the ground, you're going to save a lot of people a lot of time, and they really appreciate it. All right. So we would take these images that we collect with a fisheye lens, and we would just extract all the color data, all the intensity data from it. So this is just the brightness data we would extract here. This is called color corrected temperature, which is just how blue to red it is. So color temperature is just a way of talking about color, which is also important. And what we would do is that we would take all the light from this hemisphere of the sky, and we would integrate it to get something called scalar illuminance, which is a measure of what are you totally being exposed to on the ground. And what we wanted then is first say, okay, this is what it actually looked like on the ground from our data. This is what it looked like from the model predicted by the World Atlas. So just saying atmospheric scattering and what it looks like from space. And as you can see, this is it's smoothed out here because we have relatively coarse data. So remember, a pixel is about 750 meters on the side. And here you can see lots of much smaller amounts of variation because you can have huge changes just in the space of a few hundred meters, depending on whether or not you're being, all that light that's hitting the beach is being blocked by a hill or a building or something like that, which is one of the things we wanted to try to address. So it turns out, how do we factor in that we're getting all these different shadows and structures that are either going to be reflecting or absorbing light? And is there a way we can even estimate that from space? And the answer is yes, and it is an incredibly computationally intense problem. But what you can do is calculate something called the Skyview Factor, which is a really fancy name for this idea. If you stand here on the ground, how much of the horizon is blocked by stuff here? So if we sweep around in this entire hemisphere of the sky, how much is essentially just absorbed or reflected? But like essentially what fraction of this bubble can you see? And you can calculate and generate this. This is all done using fancy software and geospatial stuff like that. But I was able to calculate for all of Southern California over a couple of weeks. And what I was able to do is then make a new model, because that was the whole point of this, taking all the measurements I had, so all 515 beaches in Southern California, from Southern Orange County to North Ventura County, and I was able to combine the measures of how bright it was on the ground and saying, okay, this is how bright it truly looks like. Here's how bright it looks like from space. Here's what the Skyview Factor is, so how much of the sky is being blocked. And if I take those two inputs, which is the World Atlas, which is how bright does it look like from space, factoring in atmospheric scattering, how much of the horizon is being blocked by structures, what kind of model can I build that'll predict what I'm truly seeing, which is all the data I took. And the answer is you can build a reasonably accurate model. So there is scatter around this, but we found that, and this is the title of the paper, this is a really catchy title, I know, high correlation but high scale dependent variance between satellite measured night lights and terrestrial exposure, which is a great way of saying the two, we can make a model that works really well, but it varies dramatically on a very small geographic scales, which is partly what we were expecting to see. One of the other interesting things we also found was that our model is mostly unaffected by how much cloud cover there is. And why that is, I can talk about later in any questions. So we built this fancy light pollution model, and this is, by the way, what it looks like here in the Palos Verdes Peninsula. So really bright over here, and within a 10-kilometer span, it actually drops off pretty quickly. So this is about the darkest area here in the PV Peninsula. We wanted to see, well, okay, if we actually can now model from space, just knowing like the topography to calculate Skyview Factor, and we know the brightness with the World Atlas model, well, can we predict where certain species are likely to show up or not? And if we can we figure out how important light pollution is in determining where they tend to show up? So to do this becomes a really interesting problem in machine learning and analysis. And the first step is geospatial stuff, where we take all the environmental layers we can get for our region. So this is coastal California, North Ventura to South Orange County. And we ended up taking the following environmental layers, which is just elevation. So how high up you happen to be on the beach. And this is all within, we're only looking at beach ecosystems because one of the questions is just how much coastal ecosystems are being impacted by this. So we're looking at just within about 1.5 kilometers of the coast. So we're looking at elevation, we're looking at the slope, we're looking at the Skyview Factor, which is, you can essentially calculate them from elevation data. And then we can figure out distances to freshwater and saltwater, our modeled scalar illuminance, so what we're predicting how bright it should be using our model I just described earlier, how wide the beach happens to be, and then the type of beach. And the type of beach is whether or not the beach is backed by water, if it's backed by hills, if it's backed by unbuilt land or built land, that sort of thing. And our spatial resolution is 10 meters, which is actually really high resolution considering that we're dealing with a couple 100 kilometers worth of coast. So the two species we want to use are canaries in the coal mine, so to speak. One is the western snowy plover and the other one is California grunion. And we wanted to use the western snowy plover. One is an endangered species of interest that lives on California's beaches. And there is prior evidence that it tends to avoid light pollution and that it's also very skittish around a lot of other anthropogenic stressors, just like humans walking around even are going to tend to prevent them from roosting at night on the beach. The other one, another charismatic species for California, is the grunion. The spawning cycles, as far as we can tell, appear to be linked to lunar cycles, and everyone's kind of made the next jump, which is if they're linked to lunar cycles, that means they're probably going to respond in some way to light. And there's some patchy evidence that was actually generated back in the 70s. It was naval research done on this, where they found some evidence of juvenile grunions being attracted to light. There has not been a lot of work done in that field, but everyone sort of assumes like, okay, lunar cycles, we have this like one data point, they're probably going to be impacted by light some way. So what I ended up doing is first generating these maps based on what we could figure out with grunion data and plover data. And the first set here, this is 4 years worth of grunion run data, which was aggregated by Karen Martin, who actually collects a lot of community science data on grunion runs, which are essentially just marked on this 1 to 5 point Walker scale, just how many grunions are coming on shore to spawn. And even though it's a somewhat coarse scale, you're dealing with really large number of observations, so it works pretty well. And then it's saying like, okay, where beaches do we find them? And then you start generating what are known as presence points. So you're saying like, okay, like I know the beach polygon, I'm going to generate a random set of grunion points. And then that gives you your what are called presence points or observations. So we saw them on this beach. This is the beach. We're going to say like, we're going to randomly generate where they probably were. And then you generate what are known as pseudo absences. And we say pseudo absences because it's kind of the unknown unknowns. We don't know that they were never there, but considering that year after year, no one's ever seen Grunions wash ashore here, we can pretty confidently say they probably have not been there, at least in the 4-year span of this analysis. And so we generate close to 18,000 pseudo absences this way. We repeat this process with plovers. We have the roost data. This is, again, community science data in combination with some observations made by the Point Mugu Naval Air Station and the U.S. Park Service, where we tended to see plovers roosting at night. And so we took those, we again, within those roost polygons, we would randomly generate observation points. And then we would repeat the process, say like, okay, well, no one's ever seen Grunions here, at least in 4 years. Here's what we call our pseudo absences. So this is our data that we've generated here. And this is actually a relatively standard procedure in what we're about to do with modeling where you tend to see species, at least given observations. So species distribution modeling, this is the process. You get your data, so you get your presence points. You model, either you make models based on purely just presence only data, or if you're relatively confident about where things aren't, you can also generate pseudo absences. Sometimes you actually have data that has true absences if you're lucky. And then what you can do is you can go from that, you can take your environmental layers so that you can go like, okay, I happen to see these organisms here. This is what the environmental conditions were at those points. You run your species distribution model and you say, given that, and given my environmental conditions elsewhere, where else am I likely to see those species? So this is a set of machine learning models, and anybody who's worked with machine learning can roll their eyes at this point. But anyway, it's statistics. We call it machine learning. It's fine. So that's how it works. So we're using a couple of different machine learning models in our study. So the first one is just y equals mx plus b. All right, we're assuming a linear model. So basically, I know where the environmental conditions are where I happen to see things. I know where they happen. I know what it looks like where they aren't. And I fit a basic linear model. And it's always a good idea when you're doing research to run the toy test case, because sometimes the universe really is that simple. And then it's nice. The next two are actual machine learning. And one is known as max-ent, which is short for maximum entropy. And of course, its likelihood of detection is dependent on the Poisson process. Anyway, this is, to give you a quick idea here, it is a machine learning model that works if you only have presence data. So you don't even need to tell it where you didn't see things, you just need to tell it where you did see things and it'll still work. The next one is known as random forest, which you do need random points for where you don't think things were as well. But this uses a bunch of what are known as decision trees. Essentially, given your different environmental measurements, you make yes/no decisions about did you see it, did you not, did you see it, did you not, and the machine runs thousands of these to make a model about where you're likely to see things. So to do this became a fun problem in permutations, but I would randomly select a set of presence and pseudo absences for my species, and then I would split things 5 to 1, saying like, okay, 20% of my data is going to be used for evaluation, 80% for training. And so basically you're doing is saying like, if I know 80% of my data, how well can I predict the other 20%? You're looking at that given environmental conditions, you run your species distribution model, and I did this permuting it 100 times just to get an idea of like, okay, how well on average does this work? And I evaluate this. There's a whole suite of statistics here. If people want to ask me detailed questions about this, they're more welcome to. There's 5 different methods I use to evaluate it just as a sanity check, but they're all based on this idea of evaluating true positive and true negative rates, which in the age of COVID is probably something that is now at the forefront of people's mind of like, how do you really know it's there or not? But these are all various combinations of false positive and false negative. And I ran and evaluated all these models. And I looked at this for how well can I predict where Grunions or plovers were using these 3 different models, using my 5 different evaluation metrics. This table looks like a mess, less of a mess. Basically, what I found is that no matter how you evaluate it, the random forest model always turns out to give you a much more accurate description of where things are. So I went onwards with random forest here to do the next step. And I wanted to then go figure out, well, of all my environmental variables, which ones happen to be the most important? And coming back to how random forest works, what you do is you run your trees, you run your decision trees, and the tree splits with every different environmental variable here, where you go yes, no, like, was the beach backed by built land? Was the beach elevated? Was the beach at a higher low slope? And so on. And you make those decisions and go like, oh, I saw a plover. I didn't see a plover. And what you do is you run these over and over again, and you see, well, how often was the decision influenced by whether or not I had to make a decision based on, let's say, how wide the beach was? Or how often did I have to make a decision based on how elevated the beach was? And in doing that, you can start to generate what are these partial response or relative importance kind of measurements. And again, here's a huge mess of a table, but what I'm doing is saying, all right, I have all my variables here. And this is out of 100 times, how often did this measurement even show up in my final output? And how important was it relatively? And this metric here is getting in the nitty-gritty. It's related to something called a Gini coefficient. I can talk about that more if somebody really wants to get into it. But the bigger the number is, the more important it is. And I did this also for plovers. Anyway, long story short, here's what turns out to be really important. If you're looking at plovers, the distance to fresh water turns out to be important. How bright it is turns out to be really important. And how wide the beach is turns out to be really important. If you're a grunion, how bright it is and how wide the beach is turns out to be really important. So this is something that was really interesting. Of these 8 environmental variables we had, and these are really common measurements for coastal environments, it turns out that light pollution is actually near the top. The width of the beach also turns out to be important. And this is what our models actually look like. If you want to get into it, this is a heat map based on, we just overlay, we keep running this model, we run this model 100 times. The brighter it is, the more often our model passed through that point. And this pink line here is sort of your best fit through all of the noise. But what we found here, this is for plovers, is that your probability of detecting them increases as we get further from freshwater up to a point and then flattens out. And for light pollution, what we found out is that below a certain level, we tend to see them. And then all of a sudden you get to this certain threshold and it plummets. And this threshold, by the way, is about 50 millilux, which is about a quarter of the full moon. So if artificial light is bright about that, all of a sudden you're not likely to see them. And for beach width, generally we see this trend towards wider beaches, more likely to see plovers. And the best guess of that is just wider beaches, more area, less likely they're going to come across something that's going to bother them. Nothing too exciting. For grunions, it's the reverse. When it's really dark, you're not likely to see them. And all of a sudden, once you get about 100 millilux, half full moon, probability jumps up dramatically, which means that there's something about them that's attracted to light. We also saw that wider beaches more likely to see grunions. Now, the reason being is that wider beaches tend to be associated with more shallow slopes underwater, which means that it's easier for them to run ashore and spawn. So again, this isn't too surprising. But what is interesting is how important light pollution happens to be here. So in short, what did we find after all of this? And by the way, this was like 1.5 years worth of work that I just collapsed. Is that the amount of light on the ground can be reliably modeled just from space, as long as we know how bright it is from space. We have our atmospheric scattering model from the people that built the World Atlas. And if we have elevation data to build the Skyview Factor, that is like how much the sky is going to be blocked by the horizon. We found that random forest models are probably your best bet in trying to model, at least in this system, and that light pollution is really, really important in determining whether or not you see species, which is an important message if we're talking about, do we want to do things like this, where we're just going to blast light here out on the beach? And the answer is maybe not. Or you might want to change the color you're using, or other things like that. But you can't get away in saying it's not important. Basically found is, yes, it is important. All right, I want to thank a lot of people here. This was done when I was actually still a grad student at USC. But I want to thank my colleagues at USC for this. And there's a number of undergrads. I want to thank the PI of this grad, Dr. Travis Longcore, who is at UCLA. And I also want to thank these following 7 students who are on the paper, because they did work with me on it. These are students from the North Hollywood High Zoo Magnet High School. So anyway, I want to thank all of them. This is actually really amazing what we found, and I'm happy to take questions during the discussion panel. Thank you.
Thanks everyone for listening. Actually, Ariel is in the other talk happening simultaneously to this one, and you can click over there now by going to our YouTube channel and seeing the currently live streaming events. Um, and stick around. There's more to come for today. This is day 3 of Telluric Vibrations out of 5 days, which is also part of the Ars Electronica Festival for 2020. So thank you, and we'll see you later.